So we'll now discuss global and local branch predictions, two of the references, one paper by A and Pat on alternative implementations of two-level adaptive branch prediction, and chapter 9 of Shannon Lipasti. So this is the chapter from which I've taken most of the content. So first of all, we've looked at 1-bit and 2-bit predictors, but are there better predictors? For example, if we have this sequence of actual outcomes, which predictor would be good? And if we have another sequence which is repetitive, for example, which of these predictors will work well? So you can, for example, try out the 1-bit and the 2-bit predictors, and you can also try out the next ones we're going to discuss, and you'll see that we actually need better predictors than the 1 and the 2-bit to actually train this sequence. So you have a repetitive sequence, a sequence or a pattern which is repeating, and for predicting this repeating sequence, we need to have better predictors. So it's not easy to do this with 1 or 2-bit counters or 1 or 2-bit predictors, and we actually need better predictors. So what could be this better predictor? It needs to be trained for repetitive patterns. So what we can do is we can observe the history of a branch, or for example, in this case, the current outcome is fixed as per the previous two outcomes. So if the two previous outcomes were taken, the current one is not taken. So similarly here, if the two previous ones are taken, the current one is not taken, and so on. So we need some kind of a predictor which looks at the previous n history of this branch based on which it is going to predict the current outcome. So these are called as history-based predictors, and they're also called two-level predictors. So far the 1 and the 2-bit predictors that we have used are called one-level predictors because we were using the PC to directly index into the branch history table. So there was just one level. The PC is going to index into the BHT, which is going to give us the direction. But then in case of a two-level predictor, it's going to be different, and we'll see that in the next slide. So what are the two levels used in this prediction? The first level is the history. We're going to, let's say, start with 1-bit history. Of course, the history bits can be more, but let us first assume that we have a 1-bit history. So the first level is the history. And the second level is actually the counter. And this counter could be a 1-bit counter, 2-bit counter, or anything more. But we will currently assume we have a 2-bit counter. So remember that 2-bit counter is the one where we had an FSM with 4 states, and which had 4 states, which is strongly not taken, weakly not taken, strongly taken, and weakly taken. So you have to keep this at the back of your mind when you are actually going ahead with any of the future predictors that we will discuss. So two-level predictors have a 1-bit history. In this case, let us assume that we have a 1-bit history and they have a 2-bit counter. So basically they have what is called a history bit, and then they have a counter which is going to take decisions. So in a 1-bit history, what it will do is it will look at only one previous outcome. So the previous outcome of the same branch, it could be either 0 or not 0. So that is what the history bit will save. And then we are going to use the history bit to index into one of the counters. So the way it works is we'll go through this example. So let us say we have this sequence. This is an actual sequence, and we are trying to use this predictor and use these predictions and see if it actually correctly predicts or not. So I have used 1 bit of history, and because I have 1 bit of history, I can index into 2 levels in the counter. So if I have 0 or 1, I can use this bit to index into 2 options that I have for the counter. So let's say we start off with 0 as the history bit. and I'm going to have uh, two options for the counter, and each of this is a 2-bit counter. So SN means strongly not taken. So each of this counter itself is a 2-bit counter. And we have two such counters. So C and C, there are two counters. So basically I have two counters and each of them are 2-bit saturating counters. Okay, so this is just to make it look complicated, but you can actually have just 1-bit counters also to start with. But let us take this example and go through this. So let's say I have 0 as the history bit. So now what I'm going to do is I will use this to index into one of these two counters. So I have two counters here. Both of them have a state SN and SN, which is strongly not taken and strongly not taken. So if this is 0, I'm going to index into the first one. So that is going to be the prediction. Now that means that the prediction is strongly not taken, which means it is not taken. And let us say in this case that the actual outcome turned out to be taken. So which means the prediction is not correct. So we follow the same steps as we did before. First thing is, if the prediction is not correct, we will go ahead and change that counter's state. So it was strongly not taken. So I'm going to change that state to weakly not taken because this is a 2-bit counter. If this was a 1-bit counter, I would have changed it from not taken to taken. Now I've changed the state. In addition to the state, what we are going to also do is we're going to change this history bit. So what this history bit means is, what was the outcome of this branch the last time? What is the actual outcome of this branch the last time? And the last time this was taken, and therefore we're going to simply change that to 1, which means it is taken the last time. So that is what the history bit means. It means that it indicates what was the outcome of the branch the previous time. Now you would have figured out that we repeat the same steps here. Because history bit is 1, we are going to use this as an index into one of these two counters, and because it is 1, we will index into the second counter, and the second counter indicates SN. SN means not taken, strongly not taken. And let us assume that our actual outcome is also not taken. So remember that I am using this sequence T, NT, T, NT, T, and I'm simply writing that here. So because our outcomes matched with the prediction is correct. Therefore, we do not change the prediction. So we do not change the state because the state is already in strongly not taken, and the actual outcome is also not taken. So we retain the same state. So we retain the same state that is strongly not taken. But we, of course, change the history bit. The history bit is going to indicate what was the outcome the last time, and the last time the outcome was not taken. Therefore, we change it to 0. Again, we repeat the same steps. 0 indexes into the first counter, which is weakly not taken, which means it is N. The actual outcome is T. That is our third actual outcome. That is, the prediction is incorrect. Therefore, you change from weakly not taken to weakly taken, and then you change the history bit. So you keep on going. So I would recommend at this time that you pause and you complete this table, because I'm going to actually show the table in the next slide, the completed table. So you should stop at this point and try and fill up this table. So if you go on, I think I will not explain this because it is straightforward. I'll explain just one of them. So it's 1. So index it to the second counter, not taken. Prediction is right. Don't change the counter. Just change the history bit and go ahead. So with this, what you will see is after a while, after the initial training period, so this is called as the training period of the predictor. So initially, the predictor needs to get trained to the sequence. So this is also a kind of learning that the predictor does. And once it learns the pattern, you can see that the prediction is correct as it goes ahead. So this is how a two-level predictor works. So this is also called as a 1,2 predictor, which means it has a 1-bit history and it is using 2-bit counters. So if you use 1-bit history, obviously you will have 2 counters to index into, and each of these counters is itself 2 bits in nature, 1 1 or 1 0 and so on. So what is this sequence actually telling us? The sequence that we just went through, it is TNT, TNT and so on. So what this indicates is that if the last outcome was taken, you have to predict not taken right now. And if the last outcome was not taken, that is 0, you have to predict taken now. And if you actually try this out, it is going to be not working as expected. If you use a 1-bit counter, it will miserably fail. Every time it will mispredict. And if you use a 2-bit counter, it might be slightly better. That is, I'm talking of the normal 1-bit and the 2-bit counters. So therefore, you actually need this history bit along with the counter in order to predict this pattern. So this is also called 1,2 predictor. This is also called a local history based predictor. So why it is called it's a local history based predictor? Because it is only storing the history of the same branch. So every time we come across a BEQ, which is at PC equals 12, for example, you're always storing the history of the same branch. So it might not seem very obvious to you right now as to why are we even talking of same branch. We obviously want to store the outcome of the same branch. Why would we want to save the outcome of a different branch? But we will look at it later. We'll discuss later as to it might be useful to also look at the outcomes of other branches. Let's say there is a branch at PC equals 6. Maybe there is some connection of this branch to the previous branch. So therefore, it might be useful to look at a previous branch's outcome to predict the current branch's outcome. So we haven't yet looked at it. We'll look at it later. Those are called as global predictors. But right now, we have only looked at the history of the same branch. That's why it's called local history-based predictor. Now this 1,2 predictor may not work efficiently if you have a pattern like this. So this is NNT, NNT, NNT and so on. So this actually needs 2 previous history bits to be saved to predict the current outcome. And therefore, we will look at the 2-bit history, but before looking at the 2-bit history, we will look at the hardware implementation of this 2-level predictor. So you have the current PC here, and we have the branch history table, the BHT. We are assuming 8 entries in the BHT, which means that we will need 3 bits to index into it, and the 3 bits are going to come from the PC. So the 3 bits of the PC 100 are going to be used to index into this BHT. So the BHT gives us an entry. So let us currently assume that we are only saving 1 bit of history. So the BHT, unlike earlier, the BHT is not going to give us the final decision. It's only going to give us the history. This history bit is now going to be used. So let us keep the history bit here. Then we are going to have another table called the pattern history table. So this pattern history table has, let's say, 32 entries, which means that you need 5 bits to index into the PHT. So let me repeat from the beginning. We have a PC, we have a branch history table, which is going to save 1 bit of history. It has 8 entries, so you need 3 bits to index into the BHT, and the 3 bits will come from the PC. Then the history bit is going to be kept aside. We're going to have another table called pattern history table, which has 32 entries, which means you need 5 bits to index into it. 1 bit has come from this history bit. Another 4 bits are going to come from the PC again. So basically we are concatenating the history bit along with the PC to index into the pattern history table. So this is just one unique way in which you can index into this table. There might be multiple ways. So what this essentially means is that every time you get this PC and every time you get this history, you're always going to index into one particular entry. That is all it means. And if you have a certain history and a certain PC, you will always index into that particular pattern history table entry. Now in this entry, we are assuming that this is a 1-bit counter. In this particular slide, we are assuming that it's a 1-bit counter. Therefore, you have just T and NT. Now in the previous slide, we assumed that we are going to have a 2-bit counter, in which case this would be strongly taken, strongly taken, strongly not taken, weakly not taken, something like this. So in this case, this is going to contain 2 bits of entry per counter, and this is finally going to predict the direction. So the rest of the hardware is the same. You still get only 1 bit out of this pattern history table, either it is taken or not taken. And this is also going to go index into the BTB, and you will jump to the target only if this was taken, and then you will jump to the target, otherwise you will continue with PC plus 4.